In a world where the laws of classical physics no longer apply, a new realm of understanding has emerged. Welcome to the fascinating domain of quantum physics, where the strange and the unknown come together to shape our comprehension of the universe. In this chapter, we will embark on a journey to explore the fundamental principles and concepts that govern the behavior of matter and energy at the quantum level. The birth of quantum physics. The story of quantum physics begins in the early 20th century when scientists like Max Planck, Albert Einstein, and Niels Bohr started to question the long-held assumptions of classical physics. They realized that the laws of mechanics and thermodynamics, which had been so successful in explaining the behavior of macroscopic objects, failed to account for the strange phenomena observed at atomic and subatomic level. One of the key discoveries that led to the development of quantum physics was the concept of the black body radiation. In the late 20th century, scientists were studying the radiation by hot objects known as black bodies. They found that their radiation followed a predictable pattern known as the black body spectrum, which was a function of the temperature of the object. However, as the temperature increased, the radiation began to exhibit strange behavior, such as the appearance of quantized energy levels. The quantum leap. Inventor Max Planck, a German physicist, proposed a revolutionary idea to explain the black body radiation. He introduced the concept of quantum energy, which posits that energy is not continuous, but rather comes in discrete packets known as quanta. This idea was a radical contradiction which had been thought to be continuous and smooth. Planck's theory was a major breakthrough, but it was Albert Einstein who took it to the next level. Einstein proposed the concept of the photoelectric effect, which demonstrated that light itself is composed of particles, now known as photons. This idea challenged the long-held assumption that light is a wave, and it marked the beginning of the quantum revolution. The uncertainty principle. As scientists continued to explore the quantum realm, they encountered a fundamental limitation on their ability to measure certain properties of particles. This limitation, known as the uncertainty principle, was first proposed by Werner Heisenberg in counterintuitive principles, that it is impossible to know both the position and momentum of a particle with infinite position and momentum per position at the same time. The uncertainty principle has far-reaching implications for our understanding of the quantum world. It suggests that the act of measurement itself can affect the behavior of particles and that the very process of observation can introduce uncertainty into the system. This idea has been the subject of much debate and discussion among physicists, and it remains one of the most fascinating and counterintuitive aspects of quantum physics. Entanglement and superposition. Another key concept in quantum physics is the phenomenon of entanglement. Entanglement occurs when two or more particles become connected in such a way that their properties are the distance between them. This means that if something happens to one particle, it instantly affects the other, even if they are separated by vast distances. Entanglement is a fundamental aspect of quantum physics, and it has been experimentally confirmed numerous times. It has also led to the development of quantum computing and quantum cryptography, which rely on the principles of entanglement to perform calculations and encode secret messages. In addition to entanglement, quantum physics also introduces the concept of superposition. Superposition refers to the ability of particles to exist simultaneously. This means that a particle can be in two or more places at the same time or have two or more properties simultaneously. The quantum world. So, what does the quantum world look like? At the quantum level, particles are no longer discrete objects with definite positions and properties. Instead, they exist as probabilities with wave functions that describe the likelihood of finding them in different states. In this world, particles can tunnel through barriers existing in multiple places at the same time. They can also exhibit quantum behavior such as superposition and entanglement. The quantum world is a realm of probabilities where the rules of classical physics no longer apply. Quantum physics is a fascinating and complex subject that has revolutionized our understanding of the universe. From the concept of quantum energy to the uncertainty principle, entanglement, and superposition, the principles of quantum physics have far-reaching implications for our understanding energy at the quantum level. As we continue to explore the quantum realm, we are constantly reminded of the strange and counterintuitive nature of the quantum world. Yet, it is precisely this strangeness that has led to some of the most significant breakthroughs in modern physics, from the development of transistors to the creation of quantum computers. In the words of Niels Bohr, the opposite of a correct statement is a false statement. But the opposite of a profound truth may well be another profound truth. The quantum world is a realm of profound truths where the laws of classical physics no longer apply. It is a world of probabilities where particles exist in multiple states. Simultaneous measurement can affect the behavior of particles. As we continue to explore the quantum realm, we are reminded of the awe-inspiring beauty and complexity of the universe. We are also reminded of the limitations of our understanding and the need for continued exploration and discovery. The quantum world is a realm of mystery and wonder where the laws of physics are constantly being rewritten.